Greetings everyone, this is Non-Expert here back again with another video. Today we are going to be solving problem number 48 and difficulty is rated at is medium. This problem was asked by Google and let's just dive right into the problem description. So given the pre-order and in-order traversal of a binary tree, we need to write a function to reconstruct the tree. For example, if the given pre-order traversal is ABDECFG and the following in-order traversal is DVEAFCG, we need to return the following tree. And you can pause this video and check the validity of this tree. Unfortunately, we were able to find a similar problem on LeetCode, and the name of the problem is construct binary tree from pre-order and in-order traversal. And again, I would urge you to pause this video and check out the link given in the description below and try solving this problem on your own. But as you can see over here, this problem is the same problem which has been given in our daily coding problem. And before we start, we need to analyze a few things or sort of understand on how we're going to approach this problem. So as you know, the pre-order traversal, the way it sort of works is you sort of print out the root level first, then you go on the left subtree and then the right subtree. And for our in-order traversal, the way you sort of go is you go on the left-hand side, then the root, and then the right-hand side. And this is basic knowledge to all programmers. And if you don't know about in-order traversal and pre-order traversal, I would urge you to look it up. But we're sort of going to move past that and we're going to try to analyze what all we can figure out from that particular thing. So if you look at the way pre-order traversal and how it works, you know for a fact that the first element that you're going to have inside your pre-order traversal array, the first element is always going to be your root. So if you have 3 over here, 3 is going to be the root of your binary tree. And a similar approach can also be used for your in-order traversal. Whatever's the first value is always going to be the leftmost value in your binary tree. So if you have 9 over here, you know for a fact that that's the leftmost value. And the same logic sort of applies to the rightmost value in your binary tree as well. The rightmost value is 7, and in your in-order traversal, that will always be your last element, which is also 7. One other thing which you can actually use in this entire case is you can sort of subdivide a problem into understanding what is on the left hand side and what's on your right hand side. By that, what I mean is if you sort of look at the root which you have, which is 3 in this case, and you sort of find 3 in the in-order traversal array, you know for a fact that whatever comes before it is always going to be on the left side of the subtree, and whatever comes after it, which is 15, 20, and 7, that always sort of comes on the right hand side of your node 3. And that's something which we are going to be leveraging. And let's just dive right in. So over here we've been given the function build tree and we've been given 3 basic parameters. The first parameter is the self, which is not really important to us, but the other 2 parameters actually are you have a pre-order list and an in-order list. Now the way we'll be sort of going about it is we're going to use a recursive implementation, and I feel like most binary tree problems can be solved recursively, so we'll be going through that. And the way we're going to go about it is that the in-order list which we have is actually going to be spliced out for the left-hand side and the right-hand side respectively from the role which we've just created. Cool, so let's just write down a few things. So we're just going to say, hey, if in-order exists, then we need to do some pre-processing or sort of computing and so on and so forth. And our algorithm is sort of going to work on the premise that we're going to pick out the first element from a pre-order, and then we're going to find the index in our in-order, and then we're going to move forward from there. So again, we just find the index in our in-order list. So the way we can do that is by using the index function, and all we need to pass in over here is the first value in our pre-order list. Now what we'll be doing over here is that we're going to be doing a pre-order pop. And inside the pop, we're going to be passing in 0. Now this 0 is actually pretty important. If you don't really use this, what's going to happen is that the last element in the pre-order list is actually going to get popped out. And we want the first element to get popped out, then return to the index function, and that index is something that we're going to store. So in our case, you have 3 over here, and the index which you're going to store over here is going to be 1. Again, if you don't really understand why we're doing a pop, the reason for that is basically since we're going to be calling a recursive function, you know for a fact that pre-order is also going to be called. But since you're going to be calling it by reference, you need to make sure that you add the correct element. Now you can do it in a variety of ways, and you can keep a counter or a pointer, but I feel a pop sort of works in this case as well. Cool, so we have an index. Now what we need to do is we just need to create a node. So let's just create a node by using the class definition which has been given to us. And all we're going to do is we're just going to say tree node, and basically in our in order list, whatever's at the index value, that's what you're going to push in. So basically you've created a node of 3 in our case, right? And now what you need to do is you need to understand what's on the left hand side and what's on your right hand side. So let's just do that. On the left hand side, what we're going to do is we're basically going to do a recursive call of our build tree function, and over here what we're going to pass in is the pre-order list and also the in-order list, but a spliced version of the in-order list, because all we want on the left hand side is whatever elements were before our index, right? This is something which we already talked about, and the way you can sort of do that is just by doing this. What this is going to do is it's going to return an array which is all the elements before your index, and the same logic sort of applies to your node.write. So you can do self build tree, and over here instead of passing in all the elements before the index, what you need to do, you need to pass in all the elements after your index. So the way you can do that is basically you do in order index plus 1 and this particular operator, and that's basically it. And all you need to do over here at the very end is basically you need to return the node itself. And if you sort of look at the implementation, the way it's sort of working, when it sort of conjuncts all together, all the recursive calls sort of bubble up. We've sort of constructed each node, and each node has its own respective left and right elements. If it has those, if it doesn't have those, it's going to return a none, and that's how it's sort of going to move forward. Again, this is pretty simple. Let's just run this code, and hopefully this should run. Awesome, so you can see that's running. The output is the same as the expected output, and if you're facing a little bit of difficulty in understanding how it's actually working, you're sort of picking up values from the pre-order list and then just placing out your in-order traversal or your in-order into 2 different subarrays. So for over here, this is your left and this is basically your right. And what happens in this case on the right hand side, let's look at this right hand side for a while. You have 15, 20 and 7. So how do you understand what's the root over here, right? So the way to understand is that whatever element sort of comes first is basically going to be the element which you need to push over here. And that's pretty simple to understand because you just do a pre-order pop, and when you come over here, that's the first element that you encounter, and then you sort of build this entire thing out. Cool, let's just submit this solution. Hopefully there should not be any problems. Awesome, and you can see that this solution is faster than 55% of the Python online submissions. You can actually speed this up, to be very honest with you, and the reason why this is actually a little slower is actually due to this particular thing. So whenever you do a pop and you pop out the first element, you actually do it at a complexity of O of n. And the reason for that is whenever you pop out the first element, you have to still rearrange all the other elements afterwards. So due to that, the complexity of that is O of n, and you can actually, you can just use something like a D something, and let me just do that real quick. You can do a DQ, think this is the right way of writing it, and basically just set your pre-order as a DQ, and then you can do a pop left. So let's just do that. Oops. Oh yeah, so you'll have to sort of update this entire thing. You'll have to push this inside a util function. So let's just do that real quick. Just say util self pre-order in order, and the reason why I'm doing this is just so that I can set the pre-order as a DQ, and then you can just pass that thing inside. So you say DQ pre-order and just call return self dot util pre-order and in order, and you'll just have to update the recursive calls that you did. So let's just do that real quick, and you also need to update this pop to a pop left, and this operation would become an O of 1 operation. There are multiple ways of sort of enhancing the performance of this entire approach. Okay, seems to be not working. I think pop left is like this. Hopefully this should run. I don't really need to pass in any value because when you need to pop left, you pop it out, pop whatever the element at the left, and this basically runs. And when you submit this, you would see that's running at a much more faster rate. And obviously, you can improve it even further by updating this in order to a map, so that you could have a key value pair and just the indexes can be fetched easily. This dot index thing is actually working out often, and you can do that as an exercise if you want. But that's not really what's important. The important part is over here, and that's basically it. Cool. So if you do have any comments, of there's something that you did not understand, do leave it in the comment section below. And if you did like this video, do give a like and do subscribe to our channel. We have a discussion over here, and we would love to have you on board with us. And if you've already subscribed, you're awesome. We all know it. And have an awesome day. Thank you.